All right, for our next question, I'd like to look at 2004 in the Intermolecular Forces Free Response Questions assignment with you. And again, look at just a couple of the parts. There are 4 parts here. B is very similar to a question we looked at earlier, a couple of questions a couple of years ago here in the packet. C has more to do with the geometry, including a couple of the shapes that we've been looking at a bit and are pretty straightforward based on Lewis structures. But I want to look at A and D because they have a little bit more to do with intermolecular forces in a couple of different ways. So as we look at 2004 A and D again, I won't necessarily take it right through to the end on each one of these where I write out like an answer I would expect of you or one that I would hope that you would come up with. But we'll talk about it here, just kind of go through some of the high points and then sort of leave the final formulation of your answer more or less to you, all right? So when we look at question A here, we want to look at comparisons of fluorine F2 versus iodine I2. And again, in both of these, and with all of these questions, it helps if you're comparing 2 different substances to be thinking, what's the bonding type? What type of bonding is present within the molecule, intramolecular particles? Attractions, what's going on there. And then when we get beyond that, then we get into intermolecular attractions, the things that are happening between the molecules or particles of the substance. So fluorine and iodine, F2 and I2, they're both covalent. They're both purely covalent. They're perfectly non-polar covalent because in both cases, of course, they both have equal or identical electronegativities. So both of these are non-polar covalent molecules. And so they're nonpolar molecules, which means there's no dipole, there's no dipole-dipole attractions, and if there's none of that, then all that there is that basic, everybody's got it, London dispersion forces. So only intermolecular forces present here are LDFs. And again, this is sort of just a mental inventory or process that you can think yourself through without having to write it all out. But this, if you want to help us to see it written out, then I'll do that with you here. So fluorine versus iodine, if they both have intermolecular forces, we're pointing out that one is a gas and one is a solid, which means that fluorine, if it's a gas already at room temperature, it must have a much lower melting point, much lower melting point, and a much lower boiling point, because if it's a gas at room temperature, that means it's already melted and boiled, right? Iodine, on the other hand, has higher ones, and that is evidenced by the fact that at room temperature it's still a solid, so it hasn't melted or boiled yet. So it has higher renditions of both. And when we can look at these, and you can pick either one to go from here, when we can look at these higher versus lowers in comparisons with intermolecular forces, higher melting point, higher boiling point for iodine, this means that iodine has stronger or more numerous, more significant intermolecular forces than F2 does. And it would stand to reason that periodically, speaking on the periodic table, chlorine and bromine would fit in between the two of these. We've just chosen the sort of 2 extreme ends of the halogens, fluorine and iodine. So chlorine and bromine would stack nicely in the pattern in between fluorine and iodine. And we know fluorine is a gas, it says so here. Chlorine's also a gas at room temperature. Bromine's a liquid at room temperature. Iodine's a solid. So we see that gas, liquid, solid progression as we look through the halogens. But we're just going to zero in on fluorine and iodine here. So if they both have London dispersion forces, how can iodine have stronger intermolecular forces than fluorine? Well, just because they have the same kinds of intermolecular forces, those LDFs, that doesn't mean that one of them can't be more substantial than the other. And remember, LDFs, comparing LDFs means we want to compare the size of the electron cloud first, and if that's similar, then we want to look at the structures themselves. Well, F2, right, is just F2. 2 Fs bonded covalently in a single bond to each other. Iodine is I2, 2 iodines bonded covalently to each other by a single bond. So they're more or less the same. When we talk about LDFs, we're talking about the attractions, the London dispersion forces, between 2 fluorine molecules. So in between these here, the interaction between 2 F2 molecules would be LDFs. Same thing on the other side. The interaction between 2 I2 molecules would be London dispersion forces. Okay, and so there again, there's the LDFs forming an interaction or an attraction between these. And remember, London dispersion forces are simply the attractions that exist, the most basic attractions that exist between the protons of one molecule and the electrons of the neighboring molecule. That's the long and the short of what's going on. So why does fluorine seem to have weaker intermolecular forces? Why are the LDFs in fluorine weaker than the LDFs in iodine, and it has to do with that electron cloud. So remember, in a molecule of fluorine, 2 fluorines would be a total of 2 times 9 electrons each, right? So each fluorine has 9 electrons. This particle would have 18 electrons in its cloud. Iodine has 53 electrons per atom. So that's 106 electrons in a cloud. And we're talking about the cloud around sort of this iodine molecule here versus this cloud around the fluorine molecule here. And if I'm being real honest about it, our iodine cloud would be much, much larger, right? Because it has 3 additional energy levels of electrons. So fluorine's cloud would be quite small and compact. Iodine's cloud is much, much larger. So to take it through to the finish then, why does having more electrons lead to stronger London dispersion forces or more significant London dispersion forces? Well, iodine has a higher boiling point, and that's evidenced by the information they gave us about state at the beginning of the question, okay? Because it has more significant or stronger, more numerous, however you want to phrase that, LDFs than fluorine does. This is due to the fact their electron clouds are so much different in size. Okay. I2 then is more, and there's the phrase we like to try to go to when we're talking about London dispersion forces, more polarizable than fluorine, because I2 has a much larger electron cloud than does iodine, or rather than does fluorine. Maybe we should throw some numbers in there. 106 compared to fluorine with just 18. Okay. More polarizable, just to kind of connect that dot completely maybe, more polarizable equals a greater likelihood of temporary dipoles, or you might call them or see them referred to as induced dipoles. And remember, these are just dipoles that exist because the electron cloud of iodine is so much more squishy or kind of wobbly or prone to being polarized. Okay. People will struggle with this idea just a little bit. So the idea is if the electrons within that large kind of cloud of electrons in the iodine molecule, if the electrons sort of begin to sort of get a little bit of momentum within there, or they start to sort of wobble, because it's a cloud, right? It's not a firm structure. As they start to sort of move or a little bit from one side of the molecule to the other, just as they naturally would, the disorder of a molecule would let them do that. The electrons on one side, they'll start to shift toward the other side, and that makes that particle slightly, that end of the particle slightly more negative and the other slightly more positive. So in our picture up above, if we can imagine that the electrons in this molecule would just sort of naturally sort of ebb and flow toward the left, then at least for a moment that might make this side sort of slightly negative and this side slightly positive, and that would cause within the next molecule over, that next iodine molecule, that would cause the electrons to be pulled sort of toward that positive part of the first iodine molecule, and that would create momentary, temporary induced dipoles, really small, faint dipoles within these molecules. Then those are very temporary. They just kind of go and come and go and go and come and go. Because iodine has such a greater electron cloud, it's going to be a much more substantial amount of attraction and London dispersion forces than fluorine can have. So that's kind of the idea on that first question. All right, let's take a look at D. I'm gonna clear this out. Okay. And we'll look at D. We'll look at D here next. So I'm going to clear this out, and we'll be right back to join you here in a moment with part D. Okay, so let's look at part D, which has to do with ammonia, comparison of ammonia to phosphine, pH3. Not a molecule whose name you'd need to come up with off the tip of your tongue, but NH3 versus pH3. So very soluble in water, only moderately soluble, less soluble in water is pH 3. So let's start again. What kind of bonding is in NH3 and pH 3? In each of those, we're talking about nonmetals bonded to nonmetals. So these are both covalent particles. They're both covalent. That makes them sort of similar, at least at first. Let's look at their Lewis structures next. How about their polarity? Here's NH3. We've seen ammonia drawn many times. Hopefully by now you could draw that one rather quickly. Here's NH3. Nitrogen with an extra pair of electrons and 3 bonds to hydrogen. Phosphorus, same thing, actually. Phosphorus has 5 valence electrons. It'll form 3 bonds to hydrogens and have 2 electrons left of its own. So they're actually very similar Lewis structures as well, which we'd expect, both of them trigonal pyramidal, both of them in AB3E configuration. You could say both of them sp3 hybridized. But if we take it a step further now, what about polarity? What's different in terms of polarity? And hopefully you know, if you take a look at the periodic table, that nitrogen is higher up on the periodic table than phosphorus, which means it has 1 less energy level than does phosphorus. And because nitrogen has less of one less energy level, it is going to be a more electronegative element. It's going to have a stronger Coulombic pull on electrons in its bonds. It's going to be more electronegative. And you don't have a set of numbers here to look at for nitrogen and phosphorus to compare them. If you have a reference, you can go look them up and compare if you like. But knowing that the pattern of the periodic table is, or the pattern of elements is, that having fewer energy levels means you'll have a greater electronegativity when we compare elements within the same group as we do with nitrogen and phosphorus. So for nitrogen and phosphorus, we would expect that nitrogen would have a higher electronegativity than phosphorus would, and that means that within these bonds we're going to have that polarity of the electrons being sort of drawn toward the nitrogen. Okay, and so as that happens, those all add up to something, right? We're talking about a dipole now. So if we clear that back out again, our overall dipole direction in ammonia is going to be in this direction. We're going to have a slightly negative end on the nitrogen end, and we're going to have a slightly positive end down here. You could also put a slightly positive on the end of each hydrogen. But in pH 3, phosphorus is below nitrogen on the periodic table, and phosphorus has 1 additional energy level compared to nitrogen. And so phosphorus is less electronegative than nitrogen is. And so even without numbers, we would expect that in a pH bond, okay, and let's just take a look at those up close. In an NH bond, we've got a polarity that's pretty significant in this direction. Okay, this is the more electronegative element. In a pH bond, even if we don't know the numbers off the top of our head, at the very least we know phosphorus is pulling less than nitrogen is. So even if it's still stronger than hydrogen, it's going to be a weaker pull. It's going to be a far weaker polarity within that bond. And that means there's going to be a far weaker polarity within the pH 3 molecule as well, because each of these little bonds would only be a small polarity, and the overall molecule would only have a small polarity. Now, I think if you have your number sheet with the actual electronegativities nearby, if you looked them up, you'd actually find that phosphorus and hydrogen are practically identical when it comes to electronegativities. If your periodic table doesn't say they're exactly the same, it probably says they're almost exactly the same. And so what we're going to get to in that then is essentially that pH 3 is a non-polar molecule compared to NH3 for sure. So overall, this is definitely a polar molecule. This is definitely a far less, or we're going to go as far as saying simply a non-polar molecule. At least, like I say, at least far less polar than NH3. And why does that matter? Well, in order for something to dissolve into water, you have to be able to form attractions between the water molecules and the thing you're trying to dissolve. In this case, that's NH3 and pH 3. So in our answer here, we want to speak to both. Remember, this even tells us. Remember, we want to make sure we include information about both substances in your answer when you're doing comparisons as we are here. All right. So how does this come out? Well, NH3 not only is polar, hopefully you recognize that N bonded to H. This combination means that NH3 can form hydrogen bonds. Okay, so NH3 is capable of forming hydrogen bonds with water, which is also polar. And you can write hydrogen bonds as simply H bonds, okay, with water, which is another very polar molecule, and a very polar substance. Okay. And this allows NH3 to readily dissolve into water. Dissolving means you're able to form those attractions with the solvent. In this case, that's the water that's trying to separate the NH3s from each other and keep them surrounded by water molecules because of those dipole interactions or hydrogen bonding interactions or maybe just London dispersion forces. But in this case, we have the strongest of our attractions present. That's hydrogen bonding. That makes NH3 readily able to dissolve. What about pH3? The question doesn't say that pH3 is completely insoluble, so why is pH3 even a little bit soluble? Well, pH3 at the very least we know is less soluble, or sorry, less polar. And if we go as far as to say nonpolar, then it would have nothing but London dispersion forces to form interactions with water, which is possible. Okay. So we're going to go ahead and give it some benefit of the doubt. We don't know for sure. If we don't have data in front of us, we can't be real quantitative about this. Having less means to form IMFs with water molecules. So what kinds of things would pH3 be able to form? It's going to dissolve less readily in water as a result of that. But what kinds of things might pH3 be able to form with water? What kinds of intermolecular force attractions would it be able to form? Well, if it's less polar, it has a slight pole, it could form dipole-dipole attractions with water. But at the very least, pH3 would only form, at the very least, some weaker temporary dipoles. And so what we end up with, in terms of it interacting with water, would be a dipole-induced dipole sort of attraction. The dipole is in water. The temporary induced dipole, and you could just call it a temporary dipole, or instantaneous dipole, would be the only attractions that we'd have between water and pH3. Okay. How does a temporary or induced dipole work? One more quick look at that. If we have a water molecule with H2O like so, and we know that we typically like to label this end as our negative because oxygen is so much more electronegative, and this is our positive sort of an end. What happened essentially then is that pH3, being a rather nonpolar molecule, would come near a water molecule as the water tries to dissolve it, or as water is working to dissolve it. And this polarity within the water molecule would induce a temporary polarity within the pH3 molecule as well. So if we kind of imagine a pH3, I'll just sort of turn it on its side here a little bit. If we have a pH3 like so, this negative end of the molecule here in the water here would sort of cause repulsions of the electrons in the cloud around pH3. So if there's sort of a cloud, let me just kind of switch over to green here. If there's sort of a cloud of electrons around this pH3 molecule as a molecule, there'd be repulsive forces between this a permanent dipole in water. They would be repulsive forces pushing sort of against the electron cloud, and that would force the electrons across to the right side of the molecule. So that would sort of repel them and push the electrons in this direction within the molecule, and that would make this end of this molecule slightly negative because all the electrons got kind of forced in that direction by repulsions. And then just by default, that makes this end of the molecule sort of positive. And that makes here our weak attractions between water's permanent dipole, so that's a dipole, and pH3's induced or temporary dipole. That would be a very sort of insubstantial and sort of temporary attraction between water and pH3. Not nearly as significant as a permanent dipole in water and a permanent dipole in NH3, which leads to not only stronger attractions, but those hydrogen bonds that we rely on for water to do its job in so many cases as a solvent. So that's a quick run through a couple parts then of 2004. I'll leave you to sort of finish out the other ones. So that B question, again, is like a question that we saw, I think it was in 1991. And C has more to do with Lewis structures and sort of looking at ABE format and some things with bond angles and that sort of thing. So take a look at those other questions, and I'll leave 2004, at least for now, at that. Thanks for listening.